Good afternoon. Before to get on to our lecture today, let me just to make some clarity, because for some discontinuities or disturbance during our lectures in the last week and before week, I just have to make it clear that what are our course of action of the remaining days of this semester. This is a very short semester, you know that, and it's a hectic, and we have to get along double the working hours of a course in a particular week, right? And that way we were doing it. Even if you miss a day lecture, it is going to be putting us in lagging behind, and we are struggling to cope up. This is all we have seen, but I was meticulously planning so that you will not have any issues as far as learning or delivery of my lecture is concerned. Parallelly, you are also working, I'm aware that for your J component, and that reviews also are to be rescheduled. This morning I have rescheduled your reviews, and corresponding schedules that I have posted in our J component review channel. So I hope you all might have seen that the important dates for our review. So you have 3 reviews for your J component. Tomorrow we will have a review in the stipulated time from 11 to 1. There are 4 groups, so please be ready that to brief me about the title that you have proposed already, and your understanding of literatures. So it is similar to that of what we were doing during for the course vehicle dynamics. You will also do it for this vehicle crashworthiness. It is basically you're going to read for the chosen topic some few papers recent past published, and try to comprehend your idea clearly as a form of a technical paper. That's the expectation of your J component work. So your topics were already chosen, you have communicated to me, and hope that you would do good presentation to impress me tomorrow between 11 to 1. And that's for first review. And review 2 is next week again, the same time of Monday during the same time. So now 3rd August, right? Tuesday. Yeah. So next week, Tuesday, that is 10th August between 11 to 1. I have seen your free slot time, and that's why I have booked the time. And you would give your review on 2 at that time. This 1 week you would work out from the comments that I give tomorrow after listening yours, and you would almost comprehend everything and make your first draft. And with the first draft submitted to me, you will face your second review on 10th August. And that over the comments, whatever is given, all you will incorporate, and within a couple of days, 12th August, you are expected to upload yours, and we will have your final understanding or comprehension of your review. That's on 12th August. So this is how your J component assessment for 1 credit will go on now on. And as far as your digital assignment is concerned, as I have already told, it is basically how do you have listened to my video lectures and also prepared your notes. So if you have done this well, I don't think you will have a problem of your digital assignment. It's your class notes submission or discussion on it. And your quiz 1 and quiz 2 would be combined together as a comprehensive test of multiple choice question. I would prepare, and we would have that on 13th August as in the given slot time. I think in the afternoon 12 o'clock you will have your quiz, right? So this is how your internal assessment for the course would go on. Is there any doubt in that? Anything? Any doubt? So please adhere to the time, then it is convenient, right? So with that clarity on your internal assessment of digital assignment and quizzes, dates revised, and your J component assessment schedule revised. We also have to plan our remaining lectures. There are officially for this semester 28 hours of lectures required to cover the syllabus content at least. So in spite of that, it is difficult to cover up every aspects of the content of the syllabus. but I would try to maximize the delivery of mine and try to have all modules covered to the maximum possible extent in the remaining 10 hours of lectures, including today's. I have also put the schedule of lecture timing and what is that module discussion also for your convenience, so that you will not have any confusion. And why I have to shift to D1 slot from A1 slot is because of overlap of semester. I have been also allotted an A1 slot other course, so it is difficult to deliver and also to revise it for the new semester because of all registration would struck. So that is why we have to go in for. Fortunately, D1 slot you are free, so I just have shifted to D1 slot. So those 10 hours timing also I have put it in our lecture MS Teams channel. So hope you do have full clarity. I will try to adhere to all those 10 lectures possibly without any difficulties. In case if I have to cancel any one or two in that also, then I would compensate maybe in Saturday, Sundays. But however, we will try to have a good lectures to develop the content of this course, right? So with that note, let me get into today's lecture. Last class, we were just looking at, importantly, a linear spring model to understand this force due to or crash force relationship. So that has helped us to model direct central impact problem, and we were able to derive the expression for change in velocities and change in velocities, and importantly, what is that individual energy contribution to overall crush energy, total crush energy of the collision scenario by individual vehicle. That's called the partition of energies of the vehicle. So that's what we have seen in the last class. Again, that was confined to central impact. So today's class, we will look at again, how do we get this change in velocities or change in energy of an individual vehicle in order to understand non-central impact collision. And what is the final outcome of today's discussion would be, you would be able to understand the region of damage and in the vehicle during non-central impact, and you would be able to get to change in velocities of the vehicle of its mass center, right? In terms of the total crush energy, right? So, for simplicity, the total crush energy can be half times ME times V closed square, where ME is an effective mass. With two colliding vehicle, mass M1, M2, then you know what is effective mass, and half times this effective mass times closed velocity square. What is closed velocity? Closing velocity is what is the relative velocity of vehicles approaching before collision, just before collision, that square. So that is what is going to be the total crush energy, and that crush energy can be absorbed, that is dissipated. The entire absorbed energy due to the interaction of the colliding structure is dissipated. That's good for the vehicle crashworthiness. Otherwise, you would have some rebound energy that would be properly managed to avoid the severe kinematics of an occupant present inside due to crash pulse that would be induced. So this is all clear to you. Today, let's begin with our lecture to understand non-central collision. How do you represent particularly the damage region or the contact region of two vehicles, right? And how are you going to find out the force that are going to be involved in the crash, and that would further help us to go in for finding out change in velocity, and that can be expressed in terms of total crush energy. That's what is the agenda for today's lecture. So let me share my Active Inspire board. Hope you are able to see this screen. And let's quickly look at what we were doing in the last class and then get into today's lecture. So if you look at in the last lecture, number 18, we are looking at individual crush energy in vehicle-to-vehicle collision with a simplified model called, what is this model? Linear force crush distance relationship model. F is equal to Kx. And we were very much aware that it's a linear spring and the spring can have its spring force always trying to bring the spring to its free length. Accordingly, its direction will act and it becomes constant for any given value of deformation. Similarly, it can store your strain energy. But in case of crash scenario, the spring is actually undergoing a huge magnitude force exchange in a shortest duration, and that's basically of transient nature, and that would drop to zero immediately. So why? Because the spring is no more after the hit is going to act as an elastic medium. It is going to be plastic medium because in this model we consider E equals 0. E equals 0. So if you make such an assumption, then the vehicle collide and the interacting structure with the K1 and K2 of vehicle 1 and 2 respectively would deform to maximum possible deformation, and that won't regain. There won't be unloading process. So if there is no unloading, that's perfect plastic impact, right? And that is what we can understand. So this linear spring model can be used for this scenario. So if that is so, what is that energy that can be absorbed is simply half k x square. So it is from x1 to x2. If you look at from a spring, you know what is the energy that is. But that energy is not stored. That energy getting dissipated in plastic impact. So the model with the linear force crush distance relationship makes us to have mass and spring model of two simplified model of two colliding vehicle to vehicle collision can be analyzed with this model with this important points in our mind. It stands in nature. There is no energy stored. It is completely dissipated. If that is so, that helps us to going for partitioning our total crush energy as crush energy portion from vehicle 1 and crush energy portion from vehicle 2 by this ratio delta E1 by delta E2. That's going to be inversely proportional to its own stiffness. So that's what as stiffer the vehicle, the less the total crush energy absorbed can be understood from this relation, equation number 731. And we continued to look at further simplifying or manipulating our equation in terms of to write RK and RM. That's what we were doing it. So here this proportion is what is its individual vehicle crush energy compared to that of total crush energy, and that is expressed in terms of RK and RK dash. RK in terms of RK for vehicle 1, RK dash in terms of vehicle 2. If RK tends to 0, corresponds to what is corresponds to K1 by K2 is almost equal to 0, then the entire energy of the vehicle 1 is equal to the total crush energy. So that would be a scenario of rigid frontal barrier impact. So when you have a rigid frontal barrier with a stiffness infinity, that means it's a concrete rigid barrier, then there is no energy that has been absorbed by that. So entire energy absorbed, that's total crush energy, is by one vehicle, that's a colliding vehicle with the barrier. So no energy is absorbed by barrier. So this is how you could look at that equation and make your physical scenario. That's what we have seen. Then you are writing for change in velocities of an individual vehicle after collision if the vehicle is head-on-head instead of a vehicle onto barrier. So if that is so, the vector diagram helps us to get delta V1 and delta V2 in terms of delta E. And we were able to get an individual crush energies of the vehicle in terms of closing velocity. So that's what is equation 734 and 735. So in vehicle 1 and 2. So this is what we stopped in the last class. Important thing in this is we have considered two vehicle-to-vehicle collision by direct central impact. So I'm going to teach you now non-central impact. If two vehicles are colliding each other, how are you going to develop mathematical equation similar to that what we discussed in the last lecture? So this is lecture number 19. And today's date is 02/08/2021. Non-central impact. So let me draw schematically the vehicle by it from its top view, writing and drawing two rectangles. So let's look at this rectangle represent vehicle 1. This is vehicle 1. And this vehicle 1 has got a velocity v1 and that moves from left to right like this. So the vehicle motion is in this direction. And let me draw the vehicle axis, longitudinal axis. This is longitudinal axis of vehicle 1 and its center of gravity lies somewhere here. So this is C. And now look at the other vehicle. So here I'll consider this vehicle direction to the right is positive and its motion absorbed from this way to the right it's positive for this vehicle. Similarly, now the second vehicle that is going to be on this. Let me use a different color for the second vehicle. So that would be now represented like this. So look at this. Again, this is its longitudinal axis, the centroid location here for this. So this is C, and this is vehicle 2, and this has got its velocity v2 from right towards left, and this is again considered positive. For this vehicle, this is a convention. For this vehicle, this is the convention considered. See, now there is an overlap of these two vehicles that represent what is that interaction during the collision. So this is what does that we call it as the damage region or collision region. So let's call this as a collision region. This is collision region. So you would be able to say that these two vehicles drawn now would represent two vehicle head-on head approaching, but they are not at direct line. They are at some offset. So this is an offset, frontal offset impact. So what is this? Example of non-central impact problem can be frontal offset impact of vehicle collision. And this is the common region called the collision region. I would take the CG of this collision region as point P, and that is going to be this P is what is now the centroid of this contact, and that is what is going to be now our point of observation where the force during collision get exchanged. So we have to quantify that force is what is important. So the force at the contact here to get, I require an acceleration of this point is important. So the exchange of force as it start its collision event and go to its maximum deformation, then again restitution. That's what is common phenomena. But here, how this is differ from direct central impact is we look at now the centroid of vehicle 1 and centroid of vehicle 2 is not collinear, because if this is an exchange of the force, I would have my line of impact now is this. So this line of impact of two vehicle is offset to its centroid. So let's call this distance as h1. So this is h1, and this distance here is h2. H2. So 10% overlap or 20% overlap we say, right? So now H1 and H2 is centroid location from this line of impact of this colliding vehicle. And you see the centroids are not lying along the line of impact. That is why this is a case of non-central impact scenario. So this is what is the top view I have drawn. What you can observe in the top view is yaw motion. Yaw motion. So what would happen to this vehicle? So as these two vehicles collide, there will be an exchange of force at point P. To quantify that, I require to quantify an angular acceleration of an individual vehicle. And there comes a relative velocity or relative motion concept. And that is what we are going to use in today's class. And once you have this acceleration at the contact of P, you would also able to express the acceleration of the CG location in X direction. You will also have in Y direction its component, but that can be neglected as that's involvement is less. So the exchange along the line of impact to get, I require the force at point P acting to get, I require to express this acceleration of P with respect to C. And I have to get also the absolute acceleration of P. So how am I going to do is what I'm going to explain you in a while now. And before that, let's again look at what is this collision region is the region which is laterally offset a distance by H1, H2 like you have seen now. And is there any doubt at this point of time? Please ask. Otherwise, I will proceed now. Right. So let me draw again this one. So here, if you look at what is my interest point P, when they collide, the exchange of force would create what the two vehicle to rotate. So the two vehicle to rotate. So you could have watched in your impact the offset impact crash videos that after the collision you see the vehicles are not translating, they are also rotating. So the motion in yaw plane would be combination of translation and rotation. So how that is the rotation comes is because the exchange of force at point P would create a couple, yaw couple in an individual vehicle. That's the reason why it is rotating. So how are these force and yaw couple is quantified is what I'm going to explain you now. So for that, let me just draw here what would be what would be the acceleration of this point P with respect to point C. So what am I going to do? I'm just connecting point C to point P. Point C to point P. So I will have this point here and acceleration something, some arbitrary direction like that. So that is acceleration of point P. So this acceleration of point P can be resolved into two components. One is perpendicular to this bar, another one is along this. So I would have like this resolved, like this resolved. So this one is what is my interest. This one, this component is what is my interest. So this component of acceleration, that is acceleration of P with respect to C is what is I am interested in. And that is having its inclination to this line of impact as angle theta. Angle theta. So this I have drawn now acceleration of point P with respect to C for vehicle 1. And similarly, you would also have it for vehicle 2. So that would be like that. I can connect this to this. As I have drawn now, it's an identical vehicle. Maybe this is appearing C, P, C. So the C1, P, C2 is all in line. But it is not necessarily like that. If this is bigger vehicle, smaller vehicle, you would have here similar wave, whatever that I am looking at here, my acceleration, right? So let me develop further. Maybe for a clarity, I would just take this vehicle, this velocity and this acceleration vectors in a separate diagram. So let me draw an axis of vehicle 1. So this is vehicle 1. And you see here I have point C, which is CG of vehicle 1. And I have here point P, which is centroid of this damage region. So point P is center of this damage region, or you can say centroid of damage region. So this is placed where it is placed at a distance h1 offset from the axis of first vehicle. So if I connect this is my position vector. I can call R, it's a distance between this. So let me call this as R1 position vector, or distance R1, its magnitude. And now I would have my acceleration of point P with respect to point C at right angle to this position vector. At right angle to this position vector. Because if this vehicle, due to this force, impulse, would rotate about point A. So that would have acceleration of point P with respect to C, and that is relative acceleration we call. So you would also have an absolute acceleration P, absolute acceleration C. So from relative motion concept, the acceleration of P with respect to C can be written as acceleration of P minus acceleration of C. And now I wanted acceleration of P. So acceleration of P would be equal to acceleration of C, that is absolute acceleration of centroid of this vehicle, plus acceleration of P with respect to C. This is the equation. And as we have seen now here, how do I get this acceleration of P with respect to C is by knowing the angular acceleration, that is yaw acceleration. So what is my yaw acceleration here? Because of this exchange of crash impulse C forces, is because of that this would have an accelerated motion in yaw plane. Let's call that as psi double dot, yaw acceleration, psi double dot. So R into psi double dot is what is this relative acceleration. So I will have my relative acceleration given by R1 times psi double dot, right? So relative acceleration of P with respect to C, I consider as if this is an arm, or the entire vehicle would be rotating like that with respect to C. That's because of now this relative acceleration. I would be able to express my absolute acceleration of point P, right? So this is the expression. And how do you define here this yaw acceleration psi double dot as the change in yaw orientation of this CP line is what I have to consider as function of time. So second derivative of that. So it's going to be d squared psi by dt square. So that's how it will be. So what does this, any time the orientation is psi angle. So the psi is going to be function of time. So its second derivative is what is yaw acceleration. Its first derivative is yaw velocity. It's yaw orientation or yaw angle. So that's how it is. So this will be changing as function of time, and that rate of change of that its second rate is what is yaw acceleration, and r times that is what is any point on this. So suppose if I take any point in this CP, so the distance from C into this acceleration will be the acceleration. So this also would be varying linearly down. All right. So here I have some amplitude, whereas here it's zero. So lateral the acceleration at point C, AP of C at this is zero. That would increase in its magnitude proportional to this distance R1. That's what from simple kinematics of a link where one end is hinged, other end is rotating, any point on the link, its velocity acceleration can be written. That is basic mechanics. So, and that is what is used, and that is how these equations are written, right? So here what is written is all are for that point. But now what is our important requirement is what is that acceleration that go along the line of impact? That's what is important. So that is to get, I would put this AP, its component along x-axis, or acceleration at the x-axis. So I would use the notation instead of AP, x double dot P. Right? X double dot P is what is equal to x double dot C plus x double dot P of C. So similarly, y double dot, y double dot, y double dot, I can put, so that these accelerations are resolved into two components. So if you look at here, the total acceleration of this is resolved as APC, and another one is this lateral along this normal component, and that is neglected. So this only is taken. So this acceleration, x component, y component is what to get. Y component can be neglected, and x component is what is along the line of impact as playing a vital role in exchange of impulsive force. And that would be responsible for creating a couple about point C, and that is how this vehicle yaw motion takes place after the impact, right? So you have the notations from A, I change it to X here, so that you better understand. So now that's going to be equal to XC double dot plus, how do I get XP dot? Its component, right? So how do I write that? See, R psi is what is this, and there is an angle theta. That angle theta is called here projection angle. Projection angle. So I would get that here R1 psi double dot cos theta, cos theta. So let's call this equation for xp double dot, that is acceleration in horizontal direction or in along the line of impact here. Now this case is 736 equation. So now you can also refer here this angle theta can be expressed how. So see, this is 90 degrees. So this would have, if this angle is psi, if this is 90 degrees, I put this angle is going to be same as psi. And this angle is what is projection angle of this vector. So that's theta. So if this is theta, this angle is theta, because this is 90 and this sum is 90. So if this angle is theta, so what is cos theta here? Adjacent by hypotenuse, so h1 by r1. So I know here this cos theta is going to be h1 by r1, h1 by r1. So let's call this equation 7.37. So having this known, now let me rewrite this equation for xc. So equation 1 here is, so let me replace this now for psi double dot. So what would happen? Psi double dot cos theta. So r1 cos theta is now h1. So let me put that. So that's going to be xp double dot is equal to xc double dot plus r1 cos theta is h1. So h1 psi double dot. So that's equation 1. And then second equation, so that I wanted to represent what will be the acceleration at the centroidal location of vehicle 1, then it will be other way writing from this. So that's going to be xc is xp double dot minus h1 psi double dot. So whichever the acceleration, absolute acceleration. So these xp and xc are the absolute accelerations, and they are not simply they are expressed in terms of this relationship. So these two together, let's call that as equation number 7.37. 7.37. Now 37 is already mentioned here, and this is 38. 11.38. So the x component force acting on vehicle 1 and P is Fx. So now let us consider, let me go to next slide. So let's consider now the x component of the force acting during impact, acting on vehicle 1 at P during impact is, let's say, Fx. And how do you quantify this Fx? So this Fx is going to be like this. So let us just look at now this vehicle one alone for the convenient. I know this is the region of contact. This is its axis, and I have here P and C, and this distance. This is line of impact. This distance is H1. Right? So now the force Fx will be here. The force which is exerted by other vehicle onto this would be in this direction. So that's Fx. So this Fx can be replaced to its centroid. It can be brought here and I can cancel it here. So that is what is the equivalent couple system force. A single force can be represented by an equivalent force and couple at a different point. So at point P, the impulsive force Fx would be replaced by a force at point C and an associated couple. So these two would form a couple. However, the resultant, if we add these two cancels, I get only Fx. So that is what is called an equivalent force couple system. So during collision, the contact or contact zone or the damage zone, the point C, point P, the force acting would create the force at C as well as the couple at C. So force at C is going to be impulsive force, and the couple at C is going to be an impulsive couple responsible for yaw acceleration, what we have just seen in the equation. So now let me write here. Why do I consider only Fx is the force in this direction is negligible? It's negligible because that acceleration, the component you take, and that would be having more contribution towards the exchange of force in x direction. Instead, of course, there will be force in this direction Fy, but that is insignificant compared to the other effect by Fx. So you can neglect it. That's another assumption or another accountability in our derivation. So this Fx is going to be now equal to what? This Fx is written as m. So this Fx is now at point C. So that's basically the mass of this vehicle 1 into acceleration C from Newton's law. So now I can put here m1 into x double dot of C. Just now we have written in the equation 7.38. So that's going to be xp double dot minus h1 into psi double dot. So that's equation 1. This is my Fx. And what is that yaw moment? That is Fx into h1. So I would have Fx into h1 as a yaw couple, or the couple about the center of mass C, and that would be equal to I1 into psi double dot. What is I1? I1 is mass moment of inertia of the vehicle with respect to vertical axis. Correct? Mass moment of inertia of the vehicle 1 in yaw motion. In yaw motion. So how do you quantify this I1? I1 would be given by kg m1 square. kg1 kg1 square into m1. kgm into because you know the unit of mass moment of inertia is kg meter square. So it is m1 into kg1 square, where this kg1 is the radius of gyration. And this is centroidal mass moment of inertia. This is centroidal mass moment of inertia. Please note that. So this I1 is centroidal mass moment of inertia into this is what is the couple, and that magnitude would be equal to what? That would be equal to m1 k1 kg K1 I don't put, Kg1 I put to differentiate from spring constant K1 in the same early discussion. So M1 Kg1 square into psi double dot. This is equation number 2. So now let me rewrite from this the expression for yaw acceleration, that is psi double dot. That would be now fx h1 by m1 kg square, right? Fx h1 by m1 kg1 square. So fx by m1 is what is x double dot of c into h1 by kg1 square. Kg1 square. So let's say this is equation number 3, right? So the set equation 1, 2, 3, all, let us call these 3 set of equation all are 7.39 as per the textbook. I write the same number because it's easy for you to get back to the textbook and verify and confirm your understanding, right? So now let's consider 2 equation. From this equation number 39, equation 3, and from 38, equation 1, and that would again help us to simplify our derivation. So x p double dot is what is xc double dot plus h1 into psi 1 that we have seen. So in this equation, psi 1 double dot, I'm going to replace it by this. So that's going to be xc double dot plus h1 into xc double dot h1 by kg1 square. And see now h1 square, this xc double dot is common. I'll take xc double dot, I'll take it out. And that's going to be kg1 square plus h1 square by kg1 square. So I can again, from this I would be able to get what is my acceleration, linear acceleration, absolute acceleration of the point P, which is centered of the damaged region or the contact region during offset impact of the vehicle. So if this is known, I can get vice versa. Let me get my interest, that is centroidal acceleration, xc, that's going to be kg1 square by kg1 square plus h1 square into xp double dot. I just bring this on this side. So I get this, and let's call this equation as 740. All right. So now, why do I write this all? To bring in some simplification. See, now there is a factor. So here the unit and numerator and denominator is same, and I have this side acceleration is some proportion of this side acceleration. So this factor, number, is going to be now called mass reduction factor, gamma 1. So gamma 1 into xp double dot is what is xc double dot. So what is gamma 1? Gamma 1 is mass reduction factor. Mass reduction factor. And this is for vehicle 1. See, whatever that we are looking at now for vehicle 1, similar way you can look at vehicle 2 of the contact point P acceleration with respect to its one centroid, and same thing will come. The subscript 2 we will use instead of subscript 1, right? So it is similar way you will proceed and develop your equations for vehicle 2 as well. So I'm not doing that. I'm doing it only for one vehicle that you follow, right? So now xc double dot is what is equal to gamma 1 xp that we have written. So I wanted xp means it is xc double dot by gamma 1. And you see here, why is it called mass factor? You'll understand. The xc double dot is fx by gamma 1. I would xc double dot fx by m1 into gamma 1. So this is m1 into xc double dot and M1 goes off this. So XC double dot by gamma 1, I can rewrite this as like this. And this factor is multiplying with the mass. So that's why it's called mass reduction factor. That means M1 value would be further reduced because of this. That means this gamma 1 value is always less than 1. It's a fraction. That's what you understand, right? So effective mass, and this product is now what is your effective mass. So what is there in denominator? That product M1 gamma 1 is what is the effective mass of vehicle 1. You should not get confused with ME. What is an effective mass of vehicle to vehicle collision? That is accounting both the masses involved in collision. That is ME. That's also called the effective mass. But that is accounting both the vehicle M1, M2 by M1 plus M2. That's called an equivalent mass system, something that is. So that and this should not be confused. So the factor gamma 1 is simply kg1 squared by kg1 squared plus h1 squared. That comes from this relationship so far we have seen. And here that is multiplied with M1 reduces the mass, effective mass. So that's called a mass reduction factor gamma 1, and its product M1 gamma 1 is effective mass of vehicle 1. Similarly, M2 gamma 2 would be effective mass of vehicle 2. What is gamma 2, by the way? That would be kg2 squared by kg2 squared plus h2 squared. That's all. So like that analogous way you would have parallel equations. So now let me just write that again. Similarly, gamma 2 would be what? H K. Here, minute. Let us just look at. Is it H1 by this kg? Is it H1 by or kg by? Please be noted here. See this value here, whatever that I write, the fraction is h1 by this, whatever fraction that I write. So if I divide this by kg1, right? If I divide this by kg1 square, this 1 by 1 plus h1 by kg1 square. So what is that in denominator is what you have to refer. Just please make a note of it. Gamma 1 here is h1 squared by h1 squared by kg1 square. So this is h1 square. When I substitute here, just 1 minute, let me just confirm whether it is h1 squared by this or just 1 minute, give me a minute. Yeah, that's correct. I only have written my notes wrong. When I was doing it on the board, it's correct. That's kg1 squared by this, that's correct. That's correct. Okay. So similarly, you would have here, it is for gamma 2 square, gamma 2 would be kg2 squared by kg2 square plus h2 square. And you would write, similarly the relationship for xp double dot for second vehicle as well. So let's call this equation 1 and this equation 2 as set equation 7.41. If you do not follow this derivation, please ask me, I would again explain. So now please note the following important observation. So what is that is, you know that always this H1 value can be greater than 0. It cannot be less than 0, right? We consider this H1 to exist here so that it will be non-central impact. If H1 is 0, what is the meaning? H1 is 0, H2 is 0. That means the two colliding vehicle are direct central impact problem assumption was valid. So H1 greater than 0 and H2 greater than 0, then acceleration along x-axis of the center of mass will always less than that of point P, correct? So acceleration along x-axis, that is acceleration x double dot along x-axis at center of mass is always less than xp double dot. That's clear because gamma 1 is always less than 1. Gamma 1 is always less than 1. Similarly, gamma 2 is always less than 1, this fraction. Look at here, kg1 squared by kg1 squared plus h1 squared. So this is greater than this. So you would have this fraction, and this is the fact that you have your absolute acceleration in x direction of the vehicle at center. It would be smaller than that of what is that is at your xp, right? Your xp double dot. That means at the center of the damage region. So if you have understood that, now let's find out this. So I wanted to find out what I wanted to find out the change in velocities. How do I get the change in velocities of the vehicle reference to its centroid? So when I say vehicle velocity, I would always refer the velocity to the centroid of the vehicle. If that is so, I would get that simply by integration of x c double dot into dt. So integrating this acceleration at CG in x direction, I would be able to get its velocity xc dot delta xc dot refer to the velocity of centroid of that. So now r1 times this delta xp, I would have also similarly the velocity at point P. So this is the relationship. This is the relationship. So your change in velocity here is going to be r1 into delta xp. R1 into delta xp. So velocity, so the velocity v at c is going to be gamma 1 into delta vp. That's equation number 7.42. That's equation number 7.42. So the integration is integrating it over the duration of impact. That's in milliseconds, very shortest duration. So if you multiply here m1 into mxc double dot is what is the force. So I am interested in my kinematic parameter of the crash pulse. So I just integrate this crash pulse of vehicle centroid deceleration xc double dot over this shortest time interval, I would get delta xc dot, and hence I get that again in terms of delta xp dot, because we have defined the relationship through its mass factor, right? So that's clear to you. So how does this equation that comes? So this equation 47.42 comes from this. So this gamma 1 times this is the relation. So whatever this relationship that is existing for acceleration, same can be for the velocity. So you have this equation. Similarly, you would have for vehicle 2 as well. Similarly, you would have for vehicle 2 as well. And that value will be delta VC of vehicle 2 would be gamma 2 into delta VP. And that's 7.43 equation. So change in velocity, now we have it over the time period. And here again the assumption is the collision is perfectly inelastic collision or perfectly plastic collision. So the coefficient of restitution is going to be 0. So if you have that, you will add a relationship of change in velocities in direct central impact problem. Similar way you can write it for this case as well. So what we had for a direct impact problem of vehicle 1 is given by 2 times delta E total crash energy divided by M1 into 1 plus RM. So this is all you know. I don't want to repeat it again for vehicle 1. And this is what we were rewriting at. If I substitute RM as M1 by M2, this should also be represented by both masses. 2 delta E by M1 into M1 plus M2. All right. So this comes from direct central impact. But what we discuss now in this period is non-central impact, and we have got an acceleration of centroid of colliding vehicles in terms of the acceleration in x direction at the contact or the centroid of the damage region. And if that is so, I can get now at damage region, damage centroid that refer to point P at damage centroid, I would get my change in velocity of vehicle delta Vp as now simply introducing here in place of sorry, here when I put this M1, M2, so in numerator I'll have M1 by M2 also. I'll have here 2M2. This is missing. 2M2. This is going to be M1 by M2. So M1 plus M2, this M2 would go up. So there is an M2 here. So now these masses here in this equation should be replaced by its effective mass. And that effective mass is product of mass by the reduction factor. So just to substitute that here, replace these masses like this. So 2 times M2 mass, so it is gamma 2 M2. So this, what is gamma 2? It's kg2 square by kg2 square plus h2 square. That's what is gamma 2. So I just replace this mass by this effective mass into delta E by M1 would be gamma 1 M1. And here M1 M2 would be gamma 1 M1 plus gamma 2 M2. So this is that for vehicle 1. Similarly, delta Vp, change in velocity at point P during this crash duration would be given now. Here it's M2, so in this case, the second vehicle, it is 2 into gamma 1 M1 into delta E total crash energy divided by gamma 2 M2 within bracket gamma 1 M1 plus gamma 2 M2. This is for vehicle 2. So let's call this equation 7.44. And if you have this, you can also express now the change in velocity of vehicle at CG, at mass center, at mass centers. Mass centers, you have delta EC. Instead of P, I put substitute C here. That's gamma 1 into delta P1, delta Vp. So this gamma 1 to be multiplied here. If I take that inside of this radical, that's going to be gamma 1 squared in the numerator. So below there is gamma 1 that goes off. So I get my equation as 2 product of reduction factor gamma 1, gamma 2 into M2 delta E by this gamma 1 has gone off. So M1 into gamma 1 M1 plus gamma 2 M2. So this is the equation. So what is that you get? The change in velocity as function of total crush energy. And this is for vehicle 1. And for vehicle 2 also delta Vc you can write, that's gamma 2 into delta Vp. Gamma 2 into delta Vp, what is there in this? I would replace it. So gamma 2, when I bring in this radical, that's going to be in this equation, product of gamma 1, gamma 2. So the numerator in both the cases same, gamma 1, gamma 2. And here this mass is M1, not same, it's M1, here M2 is M1 into delta E by, here it's M1, so here it's going to be M2. Look at this equation, M2. And gamma 2 is gone into gamma 1 M1 plus gamma 2 M2. So this is for vehicle 2. And this set of equation, let's call equation 7.45. So I stop at this point. You have a couple of case study problems solved based on this, finding out change in velocity. So the change in velocities, if you get, you would further use this to find out the crash severity index. So like that, you can further develop based on this. But however, I would stop now teaching requirement for module 3 by this period, looking at this non-central impact scenario also to find out change in velocity at its centroid or its damaged region centroid in terms of the total crush energy. That's what we have done. In this process, we defined what are reduction factor called. On that reduction factor, gamma is given by kg square by kg square plus h1 square if it is gamma 1. It's h2 square. This is also 1. If gamma 2, then it's kg2 squared by kg2 squared by h1 square. So this is what is to be remembered. And refer to the textbook. There are some numericals involved with these formulas, and please try to solve them for exam point of view. And you can further read this chapter number 7. Interestingly, where instead of single mass and spring, you would have intermediate masses accounted. Like the frontal zone of the vehicle is not entirely crumble zone. So you have a body which is crumbling. At the same time, you have a rigid body which is not. Maybe an engine there on the chassis. So on the cradle. So that would be a lumped mass. So you can further improvise your model instead of considering single spring and mass, single mass. So like that, you have a discussion further in 7th chapter of Matthew Hume, vehicle crash mechanics. Please go through for your knowledge point of view, maybe for your literature understanding point of view. And I stop at this point the content requirement of module 3. In the next class, we will start with module 4, where we will see more of safety aspects of the vehicle. Right, that note, if you do not have any doubts, I will stop today's lecture. If you have any doubts, please ask. Otherwise, I will end the lecture. Do you have any doubts? No. Okay.